The Pauline's are good. That's usually all we get. All we get.
No, not true.
Yeah, pretty good. Where's it crazy? Just keep moving for me.
Like the cutoff based on like.
Also, I'm thinking of like the video edit.
I don't like that.
Like, I swapped my, I'm using my script.
Okay,
And I'm using them on my.
I do want to go over number 6 FRQ. I think there were some questions about that, so I want to go over that. Today, we're going to be working through pages 15 through 20. So we'll just do more Taylor series. Page 7 through 14 is particle motion, so maybe I'll save that for a little bit later. I want to just get as much practice with Taylor series since that's related to what we're going to be seeing on our test on Friday. So we'll work on page 15 through 20, but let me start off with number 6 here. So we have e to the x over 2, right? The first 4 non-zero terms about x equals 0. We know that we can build it off of our Maclaurin series for e to the x. And then once we have that e to the x built out, we can adapt for e to the x over 2, replace every x with x over 2. And we can also replace the general term x with x over 2, and that will clean up to that term. Okay, so hopefully part A is okay. Part B, use the result to show that the first 3 non-zero terms of the series for e to the x over 2 minus 1 over x. So I can take all this, which is e to the x over 2, insert it into the numerator portion, minus 1 divided by x. And I'm just trying to clean this up. Well, the nice thing is that the 1 minus 1 cancels out, and I'm just dividing every one of these terms by x. So I get 1/2 plus x over 2 to the n factorial. And also I'm dividing by x, which is really the same thing as x to the n minus 1 here. All right, so there's my general term for g of x. And part C says, for the function g in part B, find g prime of 2. Well, let's first find g prime of x. So g prime of x off of this, I'm just doing the derivative. So 1/2 goes to 0. This becomes 1 over 2 squared times 2 factorial, 2x over 2 cubed times 3 factorial. And I'm also going through power rule here. So I'm bringing down the n minus 1. Yeah, I bring down the n minus 1 and then subtracting 1. Or I can just let it be this as well. If this is my first term, I don't have to do the n minus 2. I can just just treat it like n times x to the n minus 1 to the n plus 1 times n plus 1 factorial. We just have to kind of look at this a little bit and make sure that we can adjust it to a form that will fit. All right. So there's my g prime. And then g prime of 2 up to my so g prime of 2 just basically replaces the x with 2. And so I'm left with 1 over 2 squared 2 factorial, 2 over 2 squared 3 factorial, 3 over 2 squared 4 factorial. And this is basically going to fit into that form. And they give us that form here. And we can see that it does match this n over 4 n plus 1 factorial. So we know that this is basically representing g prime of 2. And now they want us to show that g prime of 2 is equal to 1/4. And if we just rely on our derivative rules, we can just show that g prime of 2 is equal to 1/4. If we go through quotient rule and plug into, we can show that's equal to 1/4. So this n over 4 n plus 1 factorial, we can match it up with what we found with our Taylor series expansion. But then that 1/4 we can find using an older derivative method, which is in this case just quotient rule, quotient chain rule, and plug in the 2, and we get that 1/4. Okay, any other questions? Pages 1 through 6. Okay, so today we're going to work on pages 15 through 20. And again, I'm just going to pace us through the pages. And I think we should be able to get through a good chunk of it done before the class. Whatever you don't finish will be homework. And then I'll check page 15 through 20. Okay, great.
Thank
Okay, so page 15.
For part A, does it want the general terms, general term and the first four terms, or just the?
Oh, for number 1. Yeah, it's not asking for the general term. Oh, it's not asking for the general term, but we can build the general term pretty quickly just by replacing the 3x in for the x of the parent that they give us. So they gave us this parent general rule, so we can replace 3x in for that to get the new general term. And then from there, you can either go to the ratio test for interval convergence, or if you recognize that this is, oh yeah, I want to talk about that. If something fits into a geometric series, then we can just test the endpoints. But I think I should have gone through ratio test to show the interval of convergence there. Here, let me work it out using that method. Thanks. Next. Oh, sorry. My bad. Messed up there. Okay, so all we're left with is 3x. Okay, is that what you guys got after ratio test? Yeah. You're right. You're right. Yes, but our rule of sequence will be a little bit different. So yeah, that's my bad. So if I plug negative 1/3 in, the two negatives cancel out. I'm just left with P series, harmonic series that doesn't converge. But if I plug in 1/3 in, 1/3 times -3 will still leave me with an alternating harmonic series. So it does converge at 1/3. And it says find the value of the sum of -1 to the n. Now this kind of falls into that pattern here, right? This is basically following that pattern of x to the n. So if I replace -1 in for x, I can get a value for that, 1 over natural log of 1 over 1 plus 2. So natural log of 1/2. So for part B, we're just going backwards here. We know this fits into this rule here. We plug that -1 in for the x, we get something that's equivalent. So natural log of 1/2. So for part C, we know that by p series, our p series will diverge if the exponent is less than 1, and the exponent is sitting here as 2p. So we just have to set 2p less than or equal to 1, which is following the conditions for p series here. So 2p is less than 1, which is the same thing as p is less than or equal to 1/2. Sorry, less than or equal to 1. And remember, our p-value is always between, it has to be a positive value. So it has to be greater than 0, but less than or equal to 1/2. So for part D, we know 1 over n to the p will diverge between 0 and 1. But if it's 1 over n to the 2p, then p is greater than 1/2. Will converge when p is greater than 1/2, right? Because less than or equal to 1/2 will diverge, greater than 1/2 will converge. So if we want something that will diverge for the first and converge for the second, we just have to pick any p-value between 1/2 and 1. Okay, page 16. So page 16, they give you a formula to find that nth derivative for you to fill in that numerator spot of your for your Taylor polynomial. Your rule of sequence, you can just build it off of your Taylor rule here. Just replace that with the nth derivative at 5 over n factorial x minus 5 to the n. So your general term, you can just pull it from your Taylor rule, Taylor series formula. So it's a little messy to build because that nth derivative at 5, we can pull that in from what's given to us. The n factorials can cancel out, so we have a slightly cleaned up version of a sub n. This is my rule of sequence, and then just do ratio test. Limit as n approaches infinity, a sub n plus 1 divided by a sub n. Clean that up. Your n should cancel out. Multiply the 2 over first to get it into that x minus c is equal to r. This is only asking for your radius convergence. So once you get that x minus c is less than r, then whatever's on the right side is your radius. Okay. But just make sure that there's a denominator that you make that denominator go to the other side before you take out your radius. And then for part C, if I want to find the approximation for my 6th degree Taylor polynomial, I just simply have to look at the 7th unused term or 7th degree unused term. So use my rule, replace all the n with 7, and that value should be under 1 over 1,000. I know it's kind of annoying to have to multiply all this out, but you don't have to multiply it out. Multiply it out, you'll be able to see more clearly, or you just trust that this is less than 1 over 1,000 and just stop there. So, sometimes on the AP exam, sometimes you do get some values that are a little messy to multiply out. See if we can do 1 or 2 more. Okay, so page 17. This one, you're gonna build your Taylor polynomial. And then once you have your Taylor polynomial built, then you're just going to use that to approximate f of 1.5. This is a non-calculator question, so you wouldn't be expected to have to multiply and add all those numbers out. You just plug 1.5 in and leave it alone. You don't want to get it all the way down to negative 1.96. There's no need to do that. And you're not expected to clean up your value either. So even if it were a calculator section, you should be able to leave your answer on 5. Yeah, this is I don't know if there's a different calculator policy during this year, because now I'm looking at the problem thinking this is tough to do without a calculator. So, but yeah, let me walk through number 3 here. So we take our approximation, our third degree Taylor polynomial approximation, and then we do Lagrange error bound. So we use the first unused term, first unused degree, which in this case is going to be the fourth degree. So the fourth derivative evaluate at z over, we're on maximize this value over 4 factorial. My x is 1.5, my center is 2, and my n plus 1 is up to 4. They tell us that the fourth derivative evaluated x is maximized at 3. So replace that upper bound with 3. Okay. So once we get that value, that ends up being 0.008. So this is the worst case scenario in terms of how far off this approximation is. So this approximation is at most off by no more than plus or minus 0.008. So it just wants to show that this value, after we include the worst case scenario error bound, then we still guarantee that our value is going to be doesn't include -5. And if we do negative 4.96 plus 0.008 and negative 4.96 minus 0.008, we still end up with values that are less than -5. Or sorry, that's not including -5. So we know -5 is not within range of the exact value, okay? Because we have our approximation, we have our error bound, and our value is guaranteed to live somewhere between these two numbers. And neither of them include -5. The -5, sorry, is not on that interval. Okay, part C, write the fourth degree Taylor polynomial for P of X, or P of X for G of X. So G of X is f of x squared plus 2. So just take your oh, it says write the fourth degree. So okay, so we just have to worry up to the second degree, because if we replace every x with x squared plus 2, then we're going to be up to the fourth degree. And then have to just FOIL out, expand all this out, and we get g of x equals -3 plus 5x squared plus 3 half x to the fourth. And then show that g must have a relative minimum at x equals 0. And this is using second derivative test, where if I can show that g double prime of 0 is positive, then we're dealing with concave up. And if my graph is concave up and my slope is 0, I must be staring at a relative minimum. So this is second derivative test here. Okay, tomorrow I want us to do a little bit with particle motion, like BC type particle motion problems in your packet. But tonight you guys will finish up page 15 through 20. Okay. And then Thursday we'll have a class period to do a little bit more for our test review, and then our test is Friday. Okay, all right, come get the phones. Yeah.